about yet another talk on high availability and disaster recovery for MySQL. So I'm Kenny Gryp. I'm a product manager of MySQL. Been working with MySQL for, I guess, about 20 years almost. And yeah, let's get right to it. So this is mainly talking about disaster recovery, but I'll cover some high availability concepts as well. I had some demo prepared, but unfortunately, as you can see on the projectors, it's very hard to read any console, but I have some examples at least in the slides. Talking about disaster recovery, if we look at IT disasters and outages, what the main causes are, here's some data from Uptime Institute, power being one of the main reasons of an outage of a data center, or a fire, or a software error. Oh, thank you. Oh. Now, in terms of disaster recovery, costs, when there's an outage, the costs of that are rising over time. So if you compare 2019 versus 2020, there are a rising amount of companies losing more and more money. Now, some examples. Delta had a 5-hour outage a couple of years ago, and that cost them 150 million. OVH Cloud in, I think it was in France or in Germany, there was a fire, and that caused a lot of downtime, causing more than 105 million lost. That's like kind of the expected. There's many examples of this, and I think what we did in MySQL is we built some tools to make disaster recovery easy. And I'll give you a little bit of an overview on kind of how MySQL evolved kind of in the past. But first, business requirements. Very quickly, just some concepts, RTO, RPO. I suppose it's familiar for most people. So recovery time objective is how long does it take to recover from a specific failure. Recovery point objective is how much data can we lose when a failure occurs. So if you look at on the diagram here, when a failure happens is how fast can I be recovered? How long will I be down? And RPO is how much of that data from since the failure, how much data have we lost? And depending on the business requirements, there could be different RTO, RPO, depending on the application, depending on the database, and also depending on the type of failure. So when the three main types of failures that we have is high availability, and that means a single server is failing within a region. You have high availability. Maybe a network partition happens, things like that. With a disaster recovery, it's where a full region, a full network fails, a data center loses network connectivity, or there's a fire, power is lost, things like that. And then the third one, a human error, so when somebody drops the database, how do you recover from that? So I don't talk about human errors today, so normally that means recovering from a backup, doing point-in-time recovery, or using a delayed replica to speed things up, because the recovery time will be long when you have to recover your full data from a backup. So with delayed replicas, you can actually reduce that time, but kind of out of scope for today. So I'll talk mainly about high availability and disaster recovery. So let's talk a little bit about the past. And the past is very much the present, unfortunately, because there is still a lot of users of MySQL that set up replication themselves. They use multiple MySQL servers. They configure the primary they have. They set up a replica by restoring a backup, by configuring replication, adding the users, and then using all these setting up the replication themselves, using third-party applications to kind of set up a high available system. So basically what MySQL provided was only the technical pieces for this, and then leaving it up to the user to kind of set up their own environment, to set up their own high availability. And there's many flavors of kind of achieving high availability and disaster recovery. But it's mostly customized because you had to use and combine everything yourself. Even from past experience myself and knowing people that are DBAs for MySQL, a lot of the work that a DBA does is automating this setup of this architecture, setting up replication, doing all the steps. But in most cases, these architectures are quite standard and all the same. So everybody's kind of duplicating their work, right? So who's still using this kind of setup, setting up replication themselves? Who's using MySQL? Let's see that. Okay, some people. Okay, good. What do people use? Maybe some question. What do you use instead of for achieving high availability? AWS. So using a cloud service. You, for example? Okay, very customized then, right? Yeah. So this is an example where you wrote your own probably or in-house. There's also third-party tools that provide some things like MySQL Orchestrator. There was a talk about this earlier this morning where you could use Orchestrator to kind of help with some part of the automation of these things. Now, what we've done in kind of the present I'm talking about, but in fact it was since 2016, we released something called MySQL InnoDB cluster. Who's using MySQL InnoDB cluster? Okay, we have one person. Good. Let's see, hopefully I can convince more people to kind of adopt MySQL InnoDB cluster. So MySQL InnoDB cluster, just like MySQL server, open source, all the components, all the things that I'm talking about here are open source. As this is an open source conference, of course. So everything is available for everybody to use. So MySQL InnoDB cluster is a set of, like, we use all the pieces of technology that normally somebody would use, or most of them, and we make one product, one solution out of it. And we start with MySQL Server, of course, you need MySQL Server, but then what we add on top is MySQL Group Replication. So MySQL Group Replication became generally available also in 2016, along with MySQL InnoDB cluster. And what Group Replication does, it provides automatic membership changes, it handles network partitions, it guarantees consistency, no data loss when there's a failure. So Group Replication takes this next step of instead of having to use MySQL asynchronous replication, configuring semi-sync in various ways to try to make it work so you don't lose data, well, Group Replication provides all this for you. Now, Group Replication by itself, you can configure it and you can use Group Replication, but yeah, you need to configure a lot of settings and whatnot. So what we did is we have MySQL Shell, which is a new command line, well, new, also since 2015 or earlier, command line client where you can configure all of this, configure your environment. So you have MySQL client, when you use MySQL, just type MySQL, that's the MySQL client. And then MySQL Shell, which is a separate RPM or a separate package that you install, you have the MySQL Shell. And the MySQL Shell provides you with SQL interface, but also JavaScript and Python interface to kind of do these DBA tasks. So this is one of the things that the MySQL Shell does, is the installation management of such architecture. So Shell by itself also has like a logical dump and load. So if you know MySQL dump, MySQL pump, these tools are kind of single-threaded. MySQL pump is parallel, but it has a lot of issues. With MySQL Shell dump and load, we built something that dumps data in parallel, can load data in parallel, is a lot faster, has a lot of integration with S3, OCI object storage, and so on. Now, Shell, very important part, that's the user interface on how to configure this. Then we have InnoDB clone. This is one of the features that we've introduced as well around that time, where it allows you to provision a new node. So you spin up a new MySQL container, for example, and you don't have to have any data in it yet. You can just say clone, and it will clone the data from somewhere else. Using MySQL, regular MySQL connections, it takes a physical snapshot of everything and provisions the system. It's fully integrated in Group Replication. So if you add a member to the group, automatically Group Replication will try to add it. It will see it has no data, so it will use clone to kind of provide that snapshot and provision the host. The last part is the MySQL router, which is where you connect, well, you don't have to use MySQL router if you use MySQL InnoDB cluster, but it is the way on how to connect from your application to basically the database environment. And in this case, we have 3 members. We have a primary and 2 secondaries. Well, MySQL router will decide where the traffic needs to go. So I'll go into depth on a little bit of various of these areas. And what we have here is high availability. So we have RPO 0, so no data loss in case of a server failing in terms of high availability. And the time over, the recovery time is seconds. So the minimum is 5 seconds. Usually we see like 10 seconds, 30 seconds is quite normal on failover time. Now, in 2020, we introduced MySQL InnoDB replica set, and it's kind of similar in terms of architecture on how to set it up. It's very easy. You can, just like MySQL InnoDB cluster, it only takes a couple of minutes to deploy a whole entire cluster, but this is using asynchronous replication. So if you have an environment where the network is not that stable, where you're okay with some data loss, where recovery time is not that important, then you can use InnoDB replica set. So this is your classic asynchronous replication, but all automated. It's using InnoDB clone to provision hosts. It's using router integration, shell on how to configure everything. So less requirements, but using asynchronous replication, you will have a better write throughput than using group replication, which has to kind of guarantee consistency, and it does have an impact on throughput and on latency, of course. Now, introducing InnoDB cluster set, something introduced, I believe, early last year. This is a similar to, so we have MySQL InnoDB cluster, which is provides high availability. We have a set of clusters. So you can have one or multiple, and there's no limit on how many clusters you can have, clusters connecting to each other. So this is for disaster recovery. So we have, so the same high availability guarantees here, failover within seconds, no data loss. Now for when a region fails, so let's say the region Rome fails here, we need to promote the Brussels environment. So there is a couple of things. The requirements are, or the guarantees are different in that when the primary fails, it's asynchronous replication between the two. This is the most common request that we get from our users. It is okay to lose some data if the primary data center goes away. So with asynchronous replication, we are talking about seconds of data loss. That's a general. It could be more. It all depends on if there's like lack of network bandwidth. There's various things, of course, but in general, you lose kind of like a second of data, if any at all. The time to fail over is manual because it's asynchronous replication, and we cannot guarantee a split brain in this situation. It's user interaction to kind of say, make this the primary cluster. We provide all the tooling for this, so making a replica the primary is just one command. You can do a switch over, which is saying, in a healthy situation, switch over, make this the primary, the other one the replica, or you do a failover, which is this is gone, it's not healthy, I need to promote this one. We also provide fencing functions where you can say stop all write traffic or stop all read and write traffic in the network partitioned data center, for example, and then you fail over. This to reduce the split brain, of course. So we provide all these functions through MySQL shell. So it's very easy to use. If you use MySQL InnoDB cluster, then InnoDB cluster set is just similar commands on how to actually do everything. We also provide full router integration. So the router servers here, there are, let's say you have applications in both data centers. The router knows about the entire topology. When you do a failover or a switchover, the routers will be notified of the change. So the change will be pushed. Well, router both waits for notifications and also polls for changes to topology. And the router will adapt on where it needs to connect, depending on kind of what the situation is. So that makes it very easy. You just connect to router, and then router finds out the way how to connect to the database. Now, a little bit more about InnoDB cluster. So it's a single product. So the good thing is this is all developed internally within the MySQL team at Oracle. And it's basically one product. Everything is developed together. All engineering teams are aligned on what they need to do. We do full testing of the entire stack. We make sure that everything works nice and smooth with each other. It's very easy to use with MySQL shell. And when we go to group replication, so a little bit more detail here. So So it provides automatic failover. You can run it in active mode, meaning you can write to all of them at the same time. They will guarantee consistency. There are some limitations there related to, like, for example, cascading foreign keys. There are some DDL challenges to overcome, so there are still some limitations that we're aware of. We have several customers and users using it in multi-primary mode, but in general, single primary mode is the way to go. Automatic membership management, so adding and removing members is fully automatic. You just add the members with shell, you say add instance, and then it does all the rest for you. Any network partition, any failure is handled. So it's built-in conflict detection and resolution. So if two transactions are updated at the same time, if you run multi-primary, it will do certification to ensure that only one of the transactions will commit, and then the other one will be rolled back. It's the first one to commit that will be continuing, and the other one will be rolled back. So it's an implementation of replicated database state machine. So all writes are ordered within the cluster. Every member has a full data set. So it's not a kind of sharded system where as you add more members, you increase the write capacity or so. It's a way of replicating data to provide high availability. We're using XCOM, which is our own developed Paxos-based implementation to do the certification, to do the consensus. There's a lot of kind of settings that you can do. For example, you can configure the consistency levels that you want. By default, it's eventual consistency. So if you write to the primary and you read it immediately from a replica, you might see still out-of-date data. However, if you set per session or global, depending on what you want, you can enable consistency to say that when I read something, I want to make sure that it's the absolute latest. So if you read something from a secondary, it will make sure that everything that's committed on the primary will be seen as well. So it might increase some weighting on that. You can also guarantee I'm going to write a transaction, and I want to guarantee that that transaction that I write, anybody reading that data or that anybody reading needs to have that applied. So you can kind of configure it both ways. We call it before and after. So before is I want to read something, make sure it's the latest. After is I want to commit something, make sure everybody else that reads from it will have it. It is using MySQL replication by design. It's built and developed by the same MySQL engineering team, the replication team. It's making use of binary logs, relay logs, global transaction IDs. It's all built using the same. So it's been GA since MySQL 5.7. MySQL 8.0 has been GA for 5 years, starting next month, I think. So we did it we GA'd this in 2018. So consider moving to 8.0 if you're not yet. In terms of platforms, we support all platforms that we support in MySQL. So this includes Windows, Mac OS, besides Linux. So to reiterate quickly, no data loss within group replication, so RPO 0. Automatic failover, network partitions are handled. So you can do read scale out with this. You can add up to 9 members within a group. There's also flow control integrated, which means that if one of the members is lagging behind, it is possible that the primary then says, okay, I need to slow down, I need to reduce my throughput because I have a member falling behind. It's important for failover. If there's a failover and all nodes are lagging behind, failover will be slow, will take a while, or it have some impacts. So we have those consistency levels that I mentioned. Active as well. So the consensus happens through Paxos, and it is kind of one round trip. So if you commit something on the primary, they need to reach majority, basically, with the other members. So if you have 3 members, it needs to receive from one member at least that it has received that transaction. So it's one round trip to the other members. That's the added latency that you can expect. Now, in terms of MySQL router, this is how you connect your application to the database. So it does the load balancing for you. It does the connection failover if needed. It is a very lightweight daemon. It's stateless by design. authentication does not happen at router level. It always happens at the server level. There are configurations like TLS offload and connection reuse, more multiplexing. So router can multiplex multiple connections over one single connection. So if you have 200 application connections, it could reduce this to kind of like 10 connections, depending on the state of those connections. So this is some of the new features that we've introduced recently. It is still, well, more or less, not really fully anymore, but we have 2 ports, TCP ports, that are open by default, but it's customizable. One for primary traffic, and the other one for non-primary traffic to secondaries. So one is for writes and reads, and the other one is for reads exclusively. So router will forward the primary traffic to the primary only, and then the non-primary traffic to the secondaries, or the primary, depending on configuration and some scenarios. The router its configuration is mostly located in the metadata on the database itself. So there's very little to configure on the router side. It's not like when you want to change the way router behaves, you can just do it from shell, which updates the database metadata schema, and then router will see those changes and change its behavior. So that's very important. So you don't, we have customers with hundreds of router servers, you don't have to go and change all these router servers. So shell is the command line interface. So again, JavaScript, Python, SQL. You can write your own plugins. We provide a lot of tools for it. We also have the MySQL doc store that is implemented in there. And we have 2 protocols that it supports. We have the MySQL Classic protocol and the X protocol. So the X protocol is a new protocol, well, new, again, 6, 7 years old, introduced about the same time as InnoDB cluster to connect and connect to the database. We use the X protocol within this architecture for router, where in the X protocol there's something called notices, which means that the router subscribes to the metadata changes. So router says, I have a connection open, it keeps the X protocol connection open, and then when a change happens to the membership, they will send a notice back to the routers or all routers saying that, hey, the topology has changed, please update your own internal metadata. So that's why we use the X protocol. So example commands, so unfortunately the demo is very hard to read. I tried to kind of zoom it in and out, but the projector is kind of small, and black background just do not seem to work. So how do you set up a cluster? Well, you connect. We're using shell. By default, you're in JavaScript mode, so this is what we're doing as example. You just say, connect to MySQL 1, and I create a cluster object, and I say DBA create cluster, and I name it cluster. That's it. I want to configure that instance, so I want to configure the settings that I need to start group replication and all this. This is all done through shell, so you don't have to change my.cnf values anymore, because in MySQL 8 there's something called set persist only. You can restart everything through a MySQL connection. So you don't have to maintain my.cnf anymore and make sure you distribute that to all your servers. Everything can be done over a MySQL connection. Then you can add an instance. So we already have a cluster created on MySQL 1. We configure MySQL 2, and then we say add MySQL 2. And it will do everything that it needs to do. It will perform the clone, it will do asynchronous recovery, replication recovery. It will add the users, it will do all the automation for you. And then to use the router, you just bootstrap it. So you say MySQL router bootstrap, start router, and that's it. Any new members that are being added to the group, router will adapt to that automatically. Then you can check the status of your cluster. So here's an example output. It will show you there's 3 members. The primary is MySQL 1. You can see here it's using SSL. Cluster is online. We have 3 members, 2 in read-only, 1 in read-write. All of them are okay, are online. You can get more details by having extended, so more verbosity in cluster status. So there's various ways to get more data. But this is kind of the summary. Now for InnoDB replica set, it's all the same, but it's using asynchronous replication instead of group replication. So you can add as many read replicas as you want. This is perfect for read scale out, and add as much replicas as you want, or secondaries as we call it here. So this is useful for when the network is not stable, because group replication requires a stable network. If there's a lot of packet loss, if there's not enough bandwidth, group replication will suffer because of the consensus that has to happen and needs to obtain consensus for every transaction from the other nodes. Or when the requirements business requirements are pretty low on RTO and RPO. Now introducing cluster set. So we've set up a cluster. So the way to create a replica cluster is just saying cluster add replica cluster. And then you specify a host, and it creates a replica cluster. So what happens is that instead of group replication, it will just set up a new group. So adding the member to this one, it will create a new cluster, configure asynchronous replication between the two. So again, failover is manual. There is some data loss possible. It will take some time to failover because it's a manual interaction. Nothing prevents you from automating it, by the way. So it's just a single command failover. It's just one command. All of the same behavior for adding and remove nodes, remove clusters, router integration. All of this is the same. You can add 3 data centers if you want, in this case. And I think the next one, you don't even have to have 3 members in each. You can have a single member. It's not going to provide high availability within the Lisbon data center on the left, for example, but it will still work. Now, on a healthy system, the way that you would change the topology is, so for example, we have 4 routers, and they have different target modes. Let me see when I have some router slides. Okay, router integration comes later. I'll explain you a little bit what the various things that router can do. So router by default is in primary target mode. So router target primary, those 2 are in primary. So they always connect to the primary for both reads and writes. So red is writes, and then green is reads. Everything goes to the primary data center. You can set a specific target cluster. So here it's target Rome. This is target Brussels. If we want to change in a healthy situation the primary cluster, we just say set primary cluster. And what it will do is the shell will make this the primary cluster, reconfigure the replication. It will do everything necessary to guarantee that there's no split brain, no data loss, nothing. We can guarantee consistency here. And then the routers will automatically redirect their workload to kind of the new primary. I think I showed this here. So you can see that everything switched around. Replication switched around, everything in purple is kind of where things changed, and then the connections are changed. I think I forgot the red and green lines from this router to the other one. Now, router integration that we have. So, target mode primary means everything goes to the primary. Target mode Brussels, in this case, we have a Brussels data center. Brussels cluster, router will always connect to Brussels. Now, in this case, this is a read-only cluster because it's the replica. By default, but it's configurable in this release that we released in January, you can change the target, change the behavior that also, so this is the read-only port that is opened and the read-write port is closed. You can actually keep the read-write port open, but it will not accept any writes because the cluster is entirely in read-only. So there's ways to configure this. Now, you can change the target cluster by just saying, using connecting to shell to one of the nodes, creating the cluster object and say, set this router to a different target, and it will automatically change. So no need to connect to router, nothing, everything happens by updating the metadata schema. You can configure globally or per router instance the way you want it to behave. And even if, for example, there's a network partition, and this is not, let's say it's network partition and this cluster is primary, but you want to make this the primary, you can keep on serving read traffic here depending on the fencing that you configure it to. So when you use the fencing functions. which I think I have a slide on. So with 3 data centers, the same thing. You have all routers connect to the primary cluster if they have target primary. Now about the failure scenarios. So what are the scenarios that can happen? So first, the on the primary cluster. So this is high availability kicks in. So one of the secondaries in Rome will become the primary, but that asynchronous replication also needs to be reconfigured. So some of the work that we did in the replication team is basically the replica cluster is aware of all members. It's not, when we configure replication here, we don't say connect to this primary. No, we say connect to one of the nodes and fetch the whole status of it. So you can even use it when you just use regular asynchronous replication. You can configure many sources. You can even configure group replication as a source. So if we add and remove members, this one will automatically learn about this. So failover happens. I have to move back and forth here. What happens is there's a new primary elected. So let's say this one is primary. Replication will be automatically reconfigured. So no manual interaction needed. Everything will work just as expected. The same with the primary of the replica cluster. If that one fails, we also have features in group replication that make sure that when a new primary is elected, it will start the replication itself. So it will then start replication on this one. These know about the replication, knows about, it actually fetches it, the metadata, and then it can connect, it will configure replication on that new primary. So when we do fencing, so let's say there's a network partition here in Rome. There are still application servers connected because they're still in Rome as well. They're also partitioned. They might be running some batch jobs or something like that, or like a cron job. What we want to do is that we want to promote the replica cluster, but before we promote the replica cluster, we should do fencing. And we have, for example, here, fence rights is one of the commands. So you connect to this cluster, you say fence rights, it will fence all the rights. All the members will become read-only, and writes will be rejected. Reads will still be possible. We also have another command called fence all traffic, as mentioned here, and that will basically shut down the whole group. So no traffic is allowed anymore. It depends on what you want. So this is a good first step. Let's fence as soon as we can. Maybe you need to investigate some things on what went wrong, but at least you fenced early. And then you can unfence if you want, or you can do your forced primary cluster, you can do your failover. So that's forced primary cluster. It is possible to bring back this cluster. So when the network is back, it's invalidated, it's possible to rejoin it, but if writes happen, if there's a split brain, the cluster will not just rejoin. We'll have to restart a clone, remove everything. It will need to take a new snapshot to provision this host. But it is possible. So routers learn about the new topology, and one of the neat things that we have is that when the network, so we still have this invalidated fenced cluster, this router couldn't connect to the new metadata or to the new primary. Now, as soon as the network partition is resolved, routers constantly fetch from all the replica clusters and primary cluster. Oh, I have something. Is it back? Okay. I have basically I have this, this router connects to here as well, and it sees this one is the new primary. I should no longer connect to this cluster, which it was before, and then it will automatically redirect traffic there. Okay, just to recap, so we have the business requirements here. So InnoDB cluster set is good for not all requirements that you might have. And here I have a couple of slides on just saying, okay, what do I recommend? So if we have a single region, we want high availability. So you use MySQL InnoDB cluster if you want no data loss and automatic failover within seconds. If you're okay with having some data loss, to have recovery to be manual. Again, you can automate this your own, but it's dangerous because you can create split brains in all various ways. You can choose InnoDB replica set. It has the best write performance, but of course failover will take longer. If we talk about multi-region, another possibility that I haven't talked about yet is that if you want disaster recovery and you do not want any data loss, you can use 3 regions as well. And with 3 regions, you can have a single stretched InnoDB cluster deployed on 3 different regions. And you can put one member in each region, or you can put 2 members in each region. That works, 3 members as well. So if you have 2 members in each region, you have 6 total. But the good thing is that if one of the members dies in one region, there's always another one that is still going to be available. This will provide no data loss, because if it's quite unlikely that, well, it's possible that you expect, when same with high availability, you expect one failure to happen. And the failure that happens is the primary region goes away. These 2 will still be able to continue, and a new primary will be elected. You can configure weights, like I prefer this one to be primary instead of this one. So there are various settings there. So this is automatic failover. If you do 2 data centers, automatic failover is much harder because you need 3 regions basically to do this quorum to be able to do this automatically. You do need a very stable wide area network here. You don't do it over the internet, over a VPN. Latency between these networks is super important, so keep that in mind when you want something like this. But it does guarantee automatic failover, no data loss when a region fails. Now, there are some users of this. We have quite a lot of customers using this, but the majority choose MySQL InnoDB cluster, where we have high availability, no data loss, but then some manual failover with some data loss possible with InnoDB cluster set. So here's some more blog posts. I went fast today, 40 minutes. Some more information if you want to know about. We have a very good MySQL InnoDB cluster set manual. I like it a lot. It gives a lot of details on how all this operates, using the same diagrams. So MySQL shell, if you haven't tried it before, there's a lot of things there. And yeah, feel free to download and try it. Are there any questions? Because I think that's it, yeah. Any questions? No? Yes? Sir. Yes. Not affected, right? One more slide? Okay, sure. This one? This one, yes. Yeah. Yeah, so if we have this 3 regions, each one has 1 member, when I commit a write transaction on the primary, the commit will only finish and go back to the application, like commit is finished, as soon as consensus is obtained. And consensus means that the majority of them, so 2 members, have to acknowledge that they have received the transaction. So this means that if this is 20 milliseconds away, it will take 20 milliseconds before 20 millisecond round trip. It will be 20 milliseconds for every commit of a transaction. That will be added for every commit. Yeah, if this is 20 milliseconds, this is 50 milliseconds, this one will likely be first most of the time, so expect always to add 20 milliseconds. So your write performance will be affected, the latency will be affected, and possibly your throughput as well, because of that. And with InnoDB cluster set, the replication is asynchronous. So it only does consensus locally, and then asynchronously replicates to the other nodes. They don't wait till the other members have received it. So this is a kind of a most popular solution because most companies are okay with kind of these requirements. Any other questions? No? Okay, that's it. Thank you.